Okay, so in the previous video, we looked at we looked at what cis 1,2-dimethyl cyclohexane looks like. Okay, so these are the chair conformations that we should get. Something 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 kind of like this. Okay, now we're going to see what happens when we draw the trans version of 1,2 cyclomethylhexane. So basically, what we can do is we're going to draw out we're going to draw out a ring structure. Okay, so of what this will look like. So remember, trans means opposite. So, and if it's methyl, we'll have a CH3 here, CH3 here, means our H is going to go here, and our H will go here, okay? And we'll just say that this is our carbon number 1, and this is our carbon number 2. So, I assume by now that you all know how to draw the boat conformation. So this is just a matter of figuring out which. This is just a matter of just putting the substituents on. So basically, what we can do is we can draw this, right? And so remember, my rule is wedges up, dashes down. So because this methyl group is on a wedge, and I'm arbitrarily assigning it to carbon number 1, then that means that it'll have to go down over. That means it'll have to go up over here. So that's why the CH3 is going to be up like this. Okay. Now the CH3 down, and then of course that means hydrogen is on a dash, so it's going to go down. So it's going to look like that. Okay. Now, when you draw the other ones, when we draw, so let me just draw this a little easy so that it'll be a lot easier to see. So now when we draw the trans version of it, so notice that the hydrogen over here is on a wedge, so it's going up. So that means that because it's going up, it'll have to go up like that, okay? And then because the methyl is on a wedge, it's on a dash, it'll have to go down. So, okay, so right, so we drew this conformation where we have two things that are axial. Okay. Now the fact is, we're going to see what happens when we do a chair flip. Okay. So when we do the chair flip, over here, and this was from the last video. So we can swap these. So in this case, the CH3 on the number 1 carbon down here is going up. So here you have CH3. Okay, and then the number 2 carbon is on a wedge, so it's going to be going down. So if I wanted to, I could draw this maybe going down more so. So maybe I could draw it going like that or whatever. Hopefully you get the point though. So this will be my CH3 going down, and then this will be my hydrogen. Okay, so notice in this case, notice that over here we had that the methyl groups were on the were both in axial positions. Okay, and then notice that over here the methyl groups were both in equatorial positions. Okay, so now what I'm going to ask is if we can say which conformation is more stable. Is it the one where they're both equatorial, or is it the one where they're both axial? And the answer is this one. Okay? One thing to remember is that equatorial is always more stable than axial. Okay? And the reason why is because when we have something like this, and if we're to draw out the other h's or whatever, if you're to have like an h here, an h here, and an h here, so this is gauche with this, meaning that it interacts with it, causing steric hindrance, which is basically electron-electron repulsion. And also notice that there's an H over here as well, and believe it or not, this is actually going to interact poorly with this one, and this is going to interact, and then I think it's actually this one is going to repel this one, and then this one's going to repel that one. And then this one over here, or whatever, this is going to repel this one. So that's why axial is not very stable, and it's much better to have the bulkier substituent be in an equatorial position, because although it doesn't look like it, these methyl groups are not. They're not repelling each other. So I know it doesn't really look like that. But just remember as a rule of thumb that this one is going to be more stable, which means that when we look at the equilibrium, so at equilibrium, this basically means that that the arrow will mainly be pointing in the direction going from the left to the right. Because it is in fact not move stable, but more stable. So always remember that. So even if I were to just have like a really simple one, so if I were to just draw, something like this. So this is going to be more stable, okay? So because just remember this is in an axial position, and this is in an equatorial position. So always remember that, okay? Always remember that equatorial is more stable than axial. Okay, so that's why, and that's why above, in the in the reaction above, or it's not really a reaction. It's just a chair flip or whatever. The idea is that because you have axial here, you have axial here, and then you have axial here, versus on the other side when both of these were equatorial, whereby this was equatorial and this was equatorial, that this entire thing is going to be more stable. So that means that trans 1,2-dimethyl cyclo, so this is trans 1,2-dimethyl cyclo, trans 1,2-dimethyl cyclohexane is always more stable in this conformation, which is the left leaning conformation. So for the next video, I'm going to draw the different conformations for cis and trans 1,3 and 1,4. So I'm going to kindly ask you to do those on your own, and in the next video we will see, you can check your answers.